Aspettate un attimo, controllo se fa l'audio. Fa tutto insieme all'audio.
Sorry for the delay. Because an unforeseeable change because of transportation and weathercast. So I'm sorry for that. And I will now start the opening ceremony, which should really support their being of testing. About 2 or 3 years ago, I was very lost. I had just finished my bachelor's degree and was stepping into my master's. A transition that should sound straightforward, but it was not for me. The years of COVID had taken something from many of us: momentum, connection, the feeling that we were doing something that had meaning beyond the screen. And I was one of those students who struggled and I genuinely questioned whether I belonged in physics at all. Then I attended my first national ICE event, and something shifted. I found myself surrounded by people who shared the same curiosity about the world. Students from Palermo to Cardiff, from different universities, different traditions, all brought together by the same passion. I rediscovered my motivation, and I felt that I was part of something larger than myself. This experience gave me a great deal, and I swore I wanted to give something back to the community as a sign of gratitude. My name is Julia Faber. I'm a master's student at the University of Pisa, and it is my honor to stand before you as the coordinator of LoT in 2026, or for us friend, LoT. This event, everything you will experience for the next 5 days, is my attempt to offer you what was offered to me. A moment that reignites your passion, not just for physics, not just for academia, but for the people around you and where they come from. Looking at this room, I see familiar faces and some new ones. I see members of our organizing team who, after last year's edition, came back to help us with this new one. And to all of you, I extend my warmest welcome. The community changes every year, just as a participant. Every edition brings something new perspective, new ideas, but the spirit remains the same: to celebrate the International Day of Light. LoT Tuscany exists to bring together students from physics from across Europe to visit art, scientific, and cultural institutions in Tuscany and share as many applications of optics as we can and talk about our understanding of the universe. Our goal is simple: to remind you why we chose this path, to show you how much farther you can go, and to allow you to see people who can allow you to do that. But none of this would have been possible thanks to the generosity who believed us, to the people who believed us in our project from the very beginning. I want to personally thank the Department of Physics of the University of Pisa and Florence, the Scuola d'Arma Superiore, the National Institute of Nuclear Physics of Pisa, the National Institute of Optics, the European Partition Observatory, the European Laboratory of Non-Linear Spectroscopy, and the Astrophysical Observatory of Recenti. I hope this event does justice to you. And we are also deeply honored to have with us today some distinguished guests who have lent their institutional support to the LoT Tuscany. So I would like to give a word to ask to have a word from the Vice Director of the Department of Physics of Astronomy for the University of Florence, Guido Saliti, the President of Academic Program in Physics at the University of Florence, Vitaliano Giulli, and the Director of Lands and European Laboratory of Non-Linear Spectroscopy, Modugno. So, thanks for having us.
Okay, thank you for the introduction, and welcome everybody. On behalf of the Department of Physics, which is where we are now, and I don't want to spend too much time in this data, but even more than welcome, I would like to congratulate really you for this initiative, which, as I said, can be very helpful for students at this stage. So enjoy these days in Firenze. Apparently, you have good reasons to think about science because the weather doesn't allow anything different. And so welcome again.
Establish connection between Pisa and Florence that we senior people have never been able to do, so we should learn from you. No, actually, we see there are very many connections. I'm a bit joking, but not so. And I wish you a good visit to the labs and to the various institutions. We will see a nice later in the afternoon for a lab visit, and then tomorrow, if I'm not wrong, for your course. So please enjoy the conference, and thanks a lot for coming.
Finally, the president of the Talking Association of Physics students come to the stage, but they will continue to.
Exactly 4 years ago, I was sitting right there in your place, enjoying the event that would change part of my life. There I found out ASO, the Italian Association of Students, with marvelous community, which community the what you are going to live the next days, both in Florence and Pisa. A strong network of people from all over the world, not only Italy. And since I'm talking about the results, let me say something about the organizing committee. Well, you see them running around, probably stressed. Keep in mind, life of custom is not an easy event to pull off. We are talking about a clear long-term event which requires a huge logistical effort, starting from the very day the previous edition ends. So guys, they are incredible, they are dedicated, and let me say also a bit crazy to organize all of these for us. So let's give them a round of applause. I just want to ask you one thing. Use light of Tuscany to discover other people and also to be discovered. don't stay only with people that you already know, and don't be afraid to be curious. If there's one thing I like in life is that we can grow only together. We are different colors, we are different wavelengths, individual lines in a spectrum, and it's only when we overlap experiences and stories that we can create really what life. So this is the spirit of us. Welcome to LoT of Tuscany. Enjoy this project and above all, have fun. Thank you.
Let me say something because I am quite tired. First of all, sorry everyone because of my awful English. I have to go, doesn't like some like Super Mario and Super Mario. Anyway, I want to say thank you everybody for coming here in Tuscany because you know this is a place, a birth of Dante, Boccaccio, Petrarca, but also the Renaissance. So, hello. But okay, yes, we use part. Okay, let's have a second. Okay, let's go back. We have so again, what I was saying is that actually Tuscany and also Florence in particular is the place of birth of person of the culture here in Italy. This for me. But let me say some wise word for myself is actually culture should not stop. The idea of I don't know, I'm quite emotionally tired for that video. But I don't know how to speak. I'm really tired. Sorry guys, but I should go to the bathroom. For a moment, let me give the mic to go on better to you.
Well, it's your time to let again.
So I'm happy to welcome you to LoT of Tuscany. And one last thing, if you have not yet seen our program, you can see it over here, or also you can see also our side quest we're preparing for you for the next few days. There's going to be a prize at the end of the 5 days trip. Nothing huge, just a bit of appreciation. Where we will learn more about Pisa and Florence and how we see them as students over here. And with that, I finished for welcoming speech, and I would like to come to the stage Giovanni Mattiniani for his talk, and we'll give a round of applause for us.
So let's start again. And thank you again for the introduction. Let me start saying that it is a pleasure for me to speak at LoT of Tuscany for several reasons. First, because this division at the forefront of photonics, and I'm sure that you will see that with your eyes during the next days, we will visit events, we will enjoy this amazing world. But I like to speak at like Tuscany also because this region is region of movies, also many grades. Okay, so we have Pisa, Florence, and if I may add, also my hometown, Siena, this one. So this is the place where I started my study in condensed matter physics before forming a path that led me to a Sapienza University of Rome, where now I do my research on time source spectroscopy within a group that is named femtoscopy. So here you may see some faces of key members of the team, and at the end of the talk I will try to illustrate some applications of ultrafast photonics drawn directly by from our main research interests. And before we get there, I will try to illustrate some motivations to ultrafast photonics, and our main goal is to capture the atomic motions while they occur. And we can do that by an experimental approach that is named the Panko scheme, able to freeze in a photographic sense the atomic motion. And this is combined with non-linear radiation spectroscopy. That is the way to capture the very details of nuclear structures. Yeah. Okay, so introduce our goal, that is again, determine how the atom move in the natural time scale. I think that a good example is the mechanism of vision. So in the common language, we used to refer to the sentence either blink of an eye to something that is merely instantaneous, but the mechanism of vision, that is the very process that allows you to see me and me to see you right now, is something that is orders and orders of magnitude faster. Okay? It occurs thanks to a molecule that is named retina within our eyes, and of course this molecule is able to absorb the light from the sun and from the surrounding world. And when the light is absorbed, the retina is promoted from an equilibrium ground state configuration to an excited state. Okay? So here we have an electronic potential that drives the system to a structural reconfiguration that is named isomerization. And this is actually a multi-step process. Okay? There is an initial motions of some hydrogen in this chain of carbons that is followed by a torsion of several elements of the vacuum in this chain. But everything is exhausted within only 200 femtoseconds, so it's extremely fast. And this is the trigger to the nerve impulse to our brain. And you may move also outside this example. So for example, in the field of photochemistry, we have the DNA, okay, that is composed by nucleobases, the building block of the genetic material, that has been engineered by nature to screen the DNA by powerful UV radiation. And this process occurs due to a fast relaxation of the nucleobases upon the photoexcitation back to the ground state in only, again, a few hundreds of femtoseconds. You may move also to a field of photophysics, okay? And there you have amazing phenomena like light-induced phase transition, where you pump with light specific forms of the matter, and this drives the structural reorganization of novel geometries, which completely changes the physical and optical properties of the system. And again, this occurs on hundreds of femtoseconds or picoseconds. Okay, and so why the femtosecond scale is so universal? This is a simple exercise of mechanics. Okay, you know that at room temperature, the atomic speeds are only orders of thousands of meters per second, and the interatomic distances are on the order of the angstrom. So when you have relative changes, this will be on the order of tens of angstrom. And so the time required to have these changes will be simply space over velocity that is on the order of femtosecond or picosecond. And to give you a flavor of how fast is 10 femtosecond, here I'm just considering the ratio between 10 femtosecond and 1 second, that is the typical sound of the heartbeat, and this fraction is equal to the ratio between the Brownian radius and the cycle momentum. Okay, so something really small. Or if you prefer, this is also equal to the ratio between my hand and the distance between Sun and Pluto. Actually, twice this distance. Okay, so the solar system. So to access femtosecond phenomena, we have to bridge these two together. Okay, 14, 15 order of magnitude between our common life and this phenomenon. And the idea of freezing something that is moving extremely fast is historically connected to the idea of the photography. So here I show you the Boulevard du Tempo, a picture from 1838 that is widely considered as the very first picture of a landscape including a human being. Okay, so this is the human being, I hope you can see it. And this was captured because during the 10 minutes of the time of the picture, he was simply sitting there and his shoes shining. But if you look at that closer, you can see that something important is missing. What is missing up to you? Feel free to answer. This is Paris, okay, during the summer, and what do we expect to have in Paris in the middle of the summer during the day? A lot of people. Why are we missing? Try to guess, come on. They were moving too fast, correct. They were moving too fast with respect to the 10 minutes of the exposure time of the image. Okay. So of course, if you want to calculate something that is faster, you need to open the shutter for a very short amount of time. Shorter than the motion under investigation. That's it. And this brings us to the last anecdote of this presentation, related to this gentleman, that is Stanford. Okay, he has been the governor of the United States. He founded the Stanford University, but today I'm interested in him for his great passion, that were horses. Okay, he was really passionate for horse races. And at some point, he decided to answer a very debated question at the time. This is the question. Okay, it may seem trivial. The question is: are all the 4 feet of the notes of the ground during the trot or the gallop? But if you think closer to that, and also if you look at paintings before the time of Stanford, you will see picture and horses running in these very unusual postures, like flying. And the reason of this painting is because the motion of the horse running, okay, was paid for $25 at that time. But Mankiewicz started to work on that, so improving the shutter of his camera, making it quicker and quicker, and also the illusion of the films. And after several years, he came up to an experiment that is sketched here. So he had an horse running on a linear track, and at the side of the track, he placed several cameras, one after each other. Okay? And the cameras were activated by wires hit by the horse leg. And so this is what you obtain. Horse. So these are the images by Mankiewicz, okay? And one of them, of course, answered the original question by Stanford. But they said the interesting part for us is what happens if you put together all these images. Okay, you obtain this. This is the very first ultrafast movie of a running object, where ultrafast it means that it is much faster than the resolution of our eyes. And this video occurred and was recorded in 6 years of research. Of course, the field evolved. So in the 40s, we had the development of stereoscopic photography, being able to record events on the microsecond time scales, for example, a gun through an apple or through an egg. And today, what we are interested in is the study of a convolution. Okay? Something that is on the order of 10 to the minus 15 seconds, so 9 orders of magnitude faster than what stereoscopic photography reached in the images. And so to study the event so fast, we need to use the fastest thing in nature, which is light. Okay? So in laboratories today, you can synthesize beams that are short as few femtoseconds. Okay? So shorter than the dynamics under investigation. And then you can arrange them in a so-called control scheme to first trigger the dynamics of interest. So you send a light of beam, a beam of light, sorry, to a sample that starts reacting, and then while it is evolving, you use the second beam to take a snapshot, okay, of the evolving species. Of course, as I was mentioning, the PAM need to be ultra-short, so we need temporal resolution for that. The probe need to be again ultra-short, and of course, it also has to determine the geometry of the atom. So you need also structural sensitivity for the probe, and we will get there in a few slides. So the way of moving the mirrors that simply tune the optical path of one of these. So this is how to do that, and it is in some sense pretty annoying, because what you need to do is to tune the delay between the beams, PAM, probe, record, and then to repeat this operation for several delays. So today there are strategies that are trying to circumvent this issue, okay, this for loop basically. And if you are interested in that, tomorrow there will be a talk by Assemariani that is going to tell you how to circumvent this issue. And I may just point that the basic idea that is very contrary to it is to use probe pulses that are much longer than the dynamics under investigation. So that's the direction. Anyway, going back to how to record the molecular moving, we need to use the control scheme, and then, as I was mentioning, we need spatial sensitivity for our pictures. So, for that, what we can use is vibrational spectroscopy. That is something that is able to provide you with the vibrational frequency of the investigated species. So, again, let me go a step back to introduce vibrational spectroscopy, asking you what happens when you send a light beam to a sample. So here we have a video. The sample is a transparent cuvette within a liquid inside, that is cyanohexane in this case. So what happens? This is a Chinese green laser. Okay, you see it on the sample. So of course, the most portion of the laser will be what happens? You have a spot here, so this is basically it. Transmission, okay? Makes sense. Then, if you look closer at the sample, so 1 second. What is this? Why do you see a filament inside the sample? You know that? Got it? Louder? Precisely. This is an elastic scattering process. Okay? So why this is originated? It is elastic because the light that arrives to my camera in my office has the same color of the laser. Okay? And this is because when I have an electromagnetic field inside the matter, okay, the electromagnetic field is something that oscillates at the laser frequency. And so the electron clouds in the matter will start oscillating following the electromagnetic field. So basically, the electron clouds are an oscillating dipole connected to the electromagnetic field via a quantity that is named polarizability, and an oscillating dipole is something able to radiate as an antenna. Okay, so this is why we see this scattering that is named Rayleigh scattering. But then there is something even more interesting. Just 1 second. And this is what happens if you do the field. That basically suppresses the green light. Okay? You may see, I'm not sure you see it. Maybe it's, there is some light in the room, but there is inside the sample an orange filament. Okay? That is originated by an elastic scattering mechanism. Okay? And why is it course? As I was mentioning, you have an oscillating dipole, okay, that is something that radiates as an antenna, but of course at room temperature the matter is able to oscillate due to the nuclear variation degrees of freedom. And so basically this radiating dipole will oscillate also at the frequency of the matter. And when you have the problem between two periodical functions oscillating, for example, as cosine, one oscillating at the frequency of the light and one oscillating at the frequencies of the matter, you can recast this formula to the sum, again, of two periodical functions which oscillate at the frequency sum and at the frequency difference. Okay, this frequency difference is the orange light that you may not see in this picture. And this is basically the round effect. So from the world of the text from the scientist also, that discovered the process in 1928, basically this altered radiation, this orange radiation, is originated by the fluctuations of the matter around equilibrium configuration. From a quantum point of view, this may be even simpler. Okay, you know that the matter is distributed in quantum level. Okay, and so when we send the light, this can be a photon, this can be annihilated, destroyed, and you can turn this photon into a photon that has lower energy, and this energy will go to a vibrational quantum. Okay, so this is the typical appearance of a Raman spectrum. So the light diffused by a sample with several local modes. This is the Raman spectrum of carbon tetrachloride. And of course, as the normal modes are unique for a given nuclear configuration of atoms and a specific geometry, these are basically the fingerprints of the species under investigation. So you can use them to reconstruct what you are studying. And this is why they exploited for molecules as well as for solid states. So for example, here I have a picture of graphene showing that you can use Raman spectroscopy to distinguish between prism and graphene with some effects. And what we are going to see now is how to use this Raman spectroscopy approach to probe reacting atoms. Okay? So the experimental layout of the spontaneous Raman experiment at the equilibrium is this one. We have a sample, you send the light, and you look at the inelastic spectral radiation, as in the video I showed before. So you look at these lines. If you want to use this one as a probe of reacting atoms, you need to add a pump. So the pump of the pump experiment I was mentioning before, followed by this round picture. That's the idea. So again, in a very nutshell, we have a pump that promotes the system to an excited state, and while it evolves from reactant to photoproduct, you take several round snapshots. So now a question: does it work? And so I try to answer this question in this slide, showing you the Raman spectrum of fructose, this molecule, okay, obtained with a continuous wavelength. So this is something at the equilibrium. And here I show you what happens if you try to do the same with a pulsed laser. The system is still at the equilibrium, okay, you just have a short beam, that is something that would be required for doing the pump probe. So, what happens? Feel free to answer. In the figure you see at the initial time, okay, a relatively long beam, 10 picoseconds, and then these beams get shorter and shorter and shorter. What happens to the Raman spectrum? It gets what do you see? This is the original Raman spectrum, okay, with all these narrow lines, and this is it gets smoother, but it also gets broader, broader, and broader, and broader. Okay? And at a certain point, instead of all the rich information coming from this laser, you just have very congested beds. Why that? Why that? Yeah. Before you leave, okay, if you try to reduce the time duration of the beam, then you will have something that is broader than the spectrum. And so basically, if you try to take a snapshot of a system with a broadband beam, you will not collect the normal lines. You will basically convolve all the lines with the spectrum of the heart. And if you want to say from the quantum point of view, this is precisely the Heisenberg beam. Okay, you can't have at the same time spectral and temporal resolution. So to go beyond this, we need to use something that is a little bit more sophisticated than spontaneous Raman spectroscopy. And for this, we are going to see a way that exploits nonlinear vibration spectroscopy. So this was again spontaneous Raman, the experimental layout, with only one beam acting on the sample, And basically, the animation was mediated by the interaction with the vacuum field. Okay? But what you can try to do is to replace this vacuum field with an existing field. Okay? Acting on the map. If you do that, you will be able to force this run animation. And if the field that forces this run animation is ultra short, okay, so ultra broadband in spectrum, you will have a trigger of your animation that is on a femtosecond time scale, if you can do a femtosecond video to do that. Okay? And this is the very essence of stimulated ground spectroscopy that combines, in a nutshell, spectral and temporal resolution. The spectral resolution is from the narrow membrane pump, analogous to spontaneous ground spectroscopy, while the temporal resolution is determined by the ultra short beam driving the animation. And so, if at this point you combine this basically output of a chemical pump, promoting the sample to an out of equilibrium state, you will be able to perform control experiment with at the same time temporal and spectral resolution. And so, let's see this technique at work for an example. Okay, so what we started some years ago in province, okay, these are LoTs fundamental for the human life because they are responsible for the oxygen delivery to the human blood or for the oxygen storage in the muscles. And their biological role is fundamentally linked to their ability to create ligands with small cases. Okay? And here I show you the right spectrum of the myoglobin sample performed with a continuous wave laser. So this is at the equilibrium. And on the bottom you see the linear spontaneous run spectrum of this reactive beam upon the photo excitation upon 2.5 microseconds. You can see that the spectrum is, as expected, much noisier. The lines are broad, and of course you cannot access 10% time relapse because the beams is too long in time. On the right you see at more or less the same delay the spectrum obtained with nonlinear spectroscopy. And as you can see, the spectral resolution is more or less the same as the CW laser, but most importantly, you can go down to the 10% time looking at the peak position on these time scales. So, for example, here I'm focusing on the position of the line frequency round band that correspond to vibrations of the central core of the beam, which is named porphyrin ring. If we look closer at the dynamics of a few modes, so this is a mode of a collective motion of the carbon in these rings, and this is mainly related to the motion of the ion still in the central part of the project. You see some nice dynamics. Okay? So for example, in this high frequency mode, you see that there is a delayed redshift of a peak, followed by a recovery, while for the low frequency mode, you see a nearly instantaneous redshift, okay, followed by a faster recovery. And these redshifts are basically linked to the deposition of energy in our molecule. Okay? So to understand that, we need to consider what happens to a sample where you deposit energy, like energy. So, of course, we will have a population that is determined by the Boltzmann distribution. Okay? And maybe at quantum mechanics you studied this kind of system for invermonic clinic, okay, where the matter is described by an atomic potential. So in this case, all the levels of the matter will have a difference in energy that are very same, but in a real system, okay, the atomic potential is actually much more unknown. Okay, for example, if you study the more potential, you know that the spacing between eigenline levels is smaller and smaller and smaller. Okay? And this originates the spectra that you see there. Because basically, as these jumps are smaller than the bottom ones, they will be captured by the Raman spectrum as peaks that are shifted to the left with respect to the main transition. Okay? And so by looking at the redshift of this peak, you can reconstruct the population distribution of this sample. So I don't want to go into the details of that. I just want to show you what you can do with these spectra. So what you see here is not a cartoon, okay? It's a real molecular movie of a reactive beam. And as you can see, upon the photo excitation, we have the initial motion of this ion that starts going up and down, and then the energy is distributed on a 300 femtosecond time scale to the surrounding. Okay, so the carbons and the nitrogen in this ring start to vibrate, and then on a slower time scale, a couple of picoseconds, this system cools down and distributes the energy to the surrounding. Okay, so that's the dynamics of a ring and the corresponding equilibrium. So, going to the second part of the document, we may go back to the very words of Serrano, okay, the person that discovered the effect, and basically he stressed that this kind of spectra are basically originated by, let's say it again, by nuclear oscillations around the equilibrium state of the molecule. Okay, so basically, in reality, what happens to our system, to our molecules, is that they are oscillating in time around the equilibrium configuration. Okay, so the nuclei will move along the normal coordinates as a function of time. That's the very essence of the number. And actually, with the pump experiments, we can also capture in real time these motions. And the basic idea is to explore the experimental setup that I illustrated before, so the pump and probe. And to do that, you need a pump that is ultra broadband. Okay? If it is broadband, it will contain photons that have an energy difference that is equal to a Raman field. Okay, so when it occurs, by interacting with two photons with this energy difference, you will be able to create this state of the matter that is basically a superposition between the vibrational ground state and the vibrational excited level. So the final evolution of this system is simply a wave packet that is going back and forth from left to right. And this wave packet will modulate in time the optical properties of the system at the vibrational frequency. Okay, this frequency, the frequency of this energy. So of course, if we now use the probe to look at the effect of this modulation, you will be able to record a map of this kind. Okay, so you map in the real time domain the oscillation of the nuclei. Of course, if you want to retrieve the information to the frequency domain, you just have to perform the Fourier transform and then the square modulus. But now I may ask you again, do you think that this mathematical operation is straightforward, or it may cancel some information? What do you think?
Fourier transform doesn't involve the whole spectrum of frequencies, like it's limited, so it will, of course, lose some. It's not convertible, so it means that it loses some information.
So, if you go to the transfer, actually you can anti-Fourier transfer. That's just, if you have a discrete number of points, this is the fast Fourier transfer, you just have a fixed number of digits, but you can do the inverse. But here there is something that is more impacting the data that we are looking at. That is something that you require to record the information in the frequency domain. What is that? The square modulus. Why the square modulus cancel some kind of information? What it cancels? The phase, correct. The Fourier transfer of a signal is something complex. If you do the square modulus, you cancel the phase. But this is very crucial, as I will try to illustrate in the next slide, showing you an application of time domain ground spectroscopy to watch carrier dynamics from the point perspective. Okay, so if you are going to study these kind of samples that are hybrids led electroskites, they are emerging technologies for photovoltaic cells. Okay, they have a very high efficiency. Upon the photo excitation, we create holes and electrons that last for a long time with longer diffusion lengths. But as I knew, there are still some parts that are not understood about their efficiency. So what we have been doing is to study the structural dynamics upon the photo excitation of this system. So this is the absorption of this skite. And what you can basically do is to excite this system resonant or you can map below the behavior. So in this case, the sample is basically transparent, so we are just driving forms. So this is the tiny integral map upon the personal photo excitation. This is what you get if you do a Fourier transform. Okay, and if you have what happens if you do the personal photo excitation. Of course, these maps are pretty different, and maybe there is a different relative intensity with different modes. And this is basically due to a resonant excitation that determines the intensity of the lines depending on the coupling between the phons and the electron. But most importantly, there are some uniques, which I emphasize in one slide again. Those, okay? If you see two uniques that are absent in the operational photo excitation. And so what you can do, taking advantage of the information that was there in the company, you can look at the phase of these oscillations. Okay? And while for the operational excitation all the phases are more or less close to zero, upon the resonant excitation we have those two modes that are out of phase by almost 90 degrees. So what's going on? Here I try to illustrate the basic concept. So upon the injection of carriers, what you may do is simply to start a moving wave packet on the original nuclear potential, or you may alter the nuclear potential for some specific normal coordinates. Okay, because basically you injected carriers. And then if this wave packet is moving from an equilibrium configuration going back and forth, this response will give you a time domain signal that is oscillating as a sum. On the contrary, if the wave packet is moving from an out of state position of this potential, what you are going to record is an oscillation that moves as a cosine. So basically, you can use that phase information to determine if the phase that was observed in the experiment is linked to a structural configuration of the system or not. So in this kind of sample, what we identify is that there are two phones linked to the reorientation of this inorganic lattice that drive the system to a novel geometry that screen somehow the carriers from relaxation. Quanto tempo ho ancora? Okay, alright. So we can just basically skip a few slides on multi-dimensional Raman spectroscopy to conclude with some final remarks of what we have been discussing in the presentation. So I hope that I convince you that the Bank scheme is something extremely useful to capture ultra-fast phenomena. It is based on the use of an ultra-short bump able to trigger a dynamics with femtosecond time precision, followed by a femtosecond probe that again need to be ultra-short and then need to obtain a picture with a high structural resolution. And so for that we can use non-linear vibrational spectroscopy. So here you see some picture of laboratories in Korea. And the way to explore this non-linear vibrational spectroscopy can be declined in several ways. So today we have been discussing frequency domain spectroscopy, where you simply send light and then you look at the inelastically stacked radiation collecting the so-called ground spectrum, so lines in your monochromator. Or conversely, you can collect the information of the nuclear motions directly in the time domain, so that you have a wave packet that is moving, okay, in this way, and then you record a transmission of an ultrashock probe collecting the signal directly in the time domain. And so with that, I think that I may just conclude with the acknowledgement of all the people of the group where I work, the spectroscopy group, that is led by Professor Fulvio Scopino. I worked there since a lot of years. Now I'm an associate professor. Then we have Emanuele Mani, that is a very sharp researcher. Then we have several postdocs and a few PhD students. So we are having a lot of fun doing this sample experiment. And if you are curious, we have the QR code of our website here at my email. So feel free to contact me if you have some curiosities. And of course, thank you a lot for your